Okay, we'll start the next lesson now. Newton's three laws. So if you can write that down, we'll have a start. Newton's three laws. Okay, got that? Right, let's have a look. So, well, let's see who remembers this from high school, if they know it. Newton's first law. No? Eva? I know you want to try.
I remember the third one.
What's the third one?
That when two objects are in conflict.
Yeah, that's that one. Do you remember the first one?
When the stationary object.
No. Go on, yeah, maybe this, yeah. No? Anyone else? No?
It moves at a constant speed.
Okay, so you have half of it. So what's the first half? So
when an object has been applied by a force.
No, I thought you had it. Newton's first law says that if a body or an object is at rest, it will remain at rest. Or if it's in motion, if it is in motion, it moves with uniform velocity until it's acted on by a force. Okay, so in other words, wait, before you write it down, let me explain it. If this is at rest, it will stay at rest until a force is applied. Okay. If this is in uniform motion, it will stay in uniform motion until a force is applied. That's Newton's first law. Okay, so you can write it down now. And they love asking about Newton's laws on the exam. Okay, got that? Yeah? Seems familiar? Yeah? Anyone else seen this before? Kim, have you seen this before? No, this is new. You guys, have you seen this before, or is this new? What do you think, Chow? Is this new or old?
It's old.
It's old, okay.
Yeah.
New or old?
Studied before, but not too much.
Okay. Right, so, obviously, here's an example. An object at rest will remain at rest unless acted on by a force. An object will continue in a constant speed unless acted on by a force. Right, Newton's second law. Siva? Do you know this one? I know you said you knew the third one, so do you think you know the second one? Well, actually, hang on, what am I saying? Sorry. Everybody should know the second one, because we did the second one recently. F equals ma, yeah. So how could we say that as more of a sentence rather than a formula? So you could say force is... Yeah, mass of an object. So how do we say multiply? Times, yeah, times acceleration. No, you're fine. I think we usually, when we try to put in a sentence, I think we use the word product. So you could say force is the product of mass and acceleration. Okay, got that? Okay, now now's your time to shine, Siva. We're on to the third one. So, do you want to give us the third one if you remember?
Two objects that are in contact,
Yeah.
the force they exert on each other is
Equal and opposite, yeah. You're right, yeah, that's it. You can say the third law in many different ways. So the way I say it is a little bit shorter, but it's exactly the same idea. And in fact, your way is a bit more accurate. There's the force. Okay, Newton's third law. For every action, there's an equal and opposite reaction, which is what you're saying about the two objects in contact. Yeah? Okay, continue. Got that? Yeah. So here's a good example. Air is pushed out the back of the balloon and the balloon is pushed forward. So this is the action and this is the reaction. Yeah. Okay. Now, there's another important example of Newton's third law, which is called the reaction force. So look, if I drop this, gravity is pulling it down. So there's a force down, okay? So it falls, it stops. But the gravity force isn't gone. The gravity is still pulling it down. So why doesn't it move? What's stopping it from moving? The gravity is pulling it.
upward.
There's an upward force, yeah. There must be an upward force from the table that's cancelling the gravity, okay? Like here in the picture. So we call that force the reaction force. It's the force provided by the reacting object, in this case the table. Now I'd like you to draw the picture with the definition here. Yeah? Got that? Okay. Okay. Let's have a look at our first example. A block of 20 kilograms is on top of a table. What's the reaction force? Okay, so this is the picture. You have a table. You have a block. It's 20 kilograms. And there's a weight. But this is not moving. So there must be a force this way that cancels this one. So therefore, R must equal W. But W equals mg. And m is 20 and g is 9.81. So the answer is 19.62 newtons. Alright, so this is our first example. We wanted to calculate the R. Okay, so if we can write this down.
190.
Oh, sorry, thank you. Okay, you got that? Yep. Next example. A block of 200 kilograms at rest at the table. A man tries to lift the block up by using a rope, and he can pull with a force of 1,000 newtons, but the block doesn't move. What's the reaction force? Okay, so okay. 200 kilograms, man. We need to make his arm a little longer. Alright, so here is a rope, and he is pulling up with 1,000 newtons, but it doesn't move. He's not strong enough. Okay. What force is down here? Well, that's the usual one, the weight. But there's still another force here from the table. The table still has a reaction force. Okay. And this is not moving. So because it's not moving, it means that 1,000 plus the or should equal the W. Now, the reason is it's balanced. It's not moving. So the force upwards must equal the force downwards, the cancel. Balance, you know? So the or is W minus 1,000. So that's mg minus 1,000. So that's 200 times 9.81 minus 1,000. So what's that? 1962 minus 1000. Is it 962 newtons? Yeah. Yeah. Until you can pull it with enough force that the reaction becomes zero because it's left the table. Okay, got that? Yeah, continue guys. Yeah. Okay. Next one. Everything's the same except this time he makes an angle 45. Yeah. So everything's the same except this time he's pulling at an angle. So it's like this. Oh shit. So this is 200 kilograms, and here's the rope, and I should make them a different colour. Okay, and he's still pulling at a force of what did I say? 1,000 newtons. Okay, and we still have a weight here, and we still have a reaction force here, and we still have an now we have an angle of 45 degrees. Okay, so what's a little bit different here? What will I have to do differently to calculate the or? What do you think? something to do with the angle. Any ideas? Yeah. I'm going to need to change it into two components. Yeah? So this one is 1000 sine 45, and this one is 1000 cos 45. Now you see here, this force is what makes it move to the right when he pulls it, okay? But these two forces, when they add together, they must equal this to balance it vertically. Because is the block moving up off the table? No. Is it moving through the table? No. So they must balance, okay? So now we have R plus 1000 sine 45 must equal W. So the R equals mg minus, I think it's 707 here, so, Jafer's tired and hungry. It'll equal something for sure. Come on, okay. 3, 5, 5, 1255 newtons, I think. I'll make him a little bit happier now since it's moving. Okay, continue? Yep. So, next. A block of mass 73 kilograms is at rest on a rough tabletop. The man drags it at an angle. Okay, so everything looks kind of similar. I'll draw the picture for you here. So once again we have our table. This time the block is a little bit smaller. It's 73 kilograms. And we have our man. Again, he pulls at 45. So that there is 45. And the force here is 1000 newtons. But this time the table is rough, which means there's some friction force. Okay? There's some force pulling back because the table is not smooth, it's rough. And we call this force friction. Okay? And of course we still have the weight, and we still have, what's this one? Yeah, which is called the reaction. And we still should change this into 1000 cos 45, which is 1 over root 2. And this one is 1000 sine 45, which is 1 over root 2. And there's a very important point here. It says the block moves at a constant speed. So it's moving this way, constant speed. Okay. Now we know 1000 over root 2 plus R should equal W, the weight, yeah. But what about the friction? Does it equal this? Or is this bigger than the friction because it's moving to the right? What do you think? I think it's bigger because it's moving to the right. That's not true. the friction should equal 1000 over root 2. But I want someone to tell me why. Yeah. Newton's first law. Newton said if it's at rest, it'll stay at rest. If it's moving at a constant speed, it will stay at a constant speed. So the point of Newton's first law is that being at rest is the same as moving at a constant speed. There's no force on you. So these two must be equal to make no force, to cancel it. That moving at a constant speed is the same as being at rest. There's no force. Do you understand? Kim, you don't look happy. Do you understand? No, that's okay. You can tell me this. Yeah. So this is what Newton's first law says. So if this guy is at rest, it means that there's no force. If there is a force, like say here 10 newtons, then there must be a force here of 10 newtons, because in total we should have no force if it's at rest. But Newton also said that this is the same as if this is moving with a constant speed. That's like being at rest. And if there is a force, then it must cancel this. And if there is a force, it must cancel this. That being at a constant speed is like being at rest. That there isn't really a difference. Yeah? Which I know seems a bit strange, because you really feel like if it's moving, there should be a force. Right? It really feels like if this is moving, there should be a force. But no, remember, there's only a force if it's accelerating. If it's accelerating. Okay, so back to this now. So can I calculate R? Easily. Can I calculate friction? Yeah. The friction, I think this is 707 newtons. And the R here, the R will equal W minus that, which I think, it's the same answer I got before. I think it's 1255 newtons. Yeah? Is that 1255? Oh, sorry, it's not 1255. I'm sorry, because it's 73 kilograms, not 200 kilograms. What is it actually? So 73 times 9.81 minus 707. Nine point one three newtons. Okay, thank you. Continue. continue, guys, or do you need more time? I can continue. Now, I actually. That question is very similar to one that's in the book, which I want you to try by yourself. But I'll just tell you something that would be helpful, okay? How can I draw this? You stand on it, and it has a number here. Now, what is this called? What are these called? Weighing scales. Yeah? What does it measure? Yeah, it doesn't actually. I mean, we say it's weight, but when we think about it, weight is equal to mg. And what unit is mg? Newtons. It's in newtons, isn't it? So a weighing scale doesn't measure your weight, because if it measured your weight, it should give you the number in newtons. So instead, what does a weighing scale really give you? Gives you your mass, because it'll tell you what you are in kilograms. Okay, so we shouldn't really call it a weighing scale. We should call it, I don't know, a mass scales or something. Anyways, it gives you the mass, right? Now, how does it calculate your mass? Yeah, good too, yeah. I mean, does it scan your body to see what your mass is? No. How does it get your mass? How does it figure it out?
From the force?
Yeah, from the force. Yeah. Which force now?
Weight force?
From your weight force. Yeah, now that's what you think. That's what I used to think. But then when I was thinking about this, I realised, no, it's not actually your weight that it measures. It's actually the reaction force. Now you might say, well, what's the difference? Because if you're not moving, the R equals the W. So you say, so what's the big deal? If you're not moving, it doesn't matter. It's the same thing. Well, in this example, what I've done is I put the person inside an elevator, and the elevator is moving up. And that's going to actually change the number here. Will it say more or less? Will it be bigger or smaller?
Smaller.
No, it'd be bigger. Because think about it, when you move up in a weighing scale, in a lift, you feel like you're pushing into the ground more. Number 6 is an interesting one. I'll let you try and figure it out, okay? So what I want you to do, you should be able to do 1 to 5 with not too much trouble. But number 6 is an interesting one. Very interesting one. I'm very happy that I thought of that question. I imagined it up one day. Okay, so if you can start those, if you can do those for what's it, 9-8 minutes, and then we'll finish, okay? Yeah, well, we're going to have a tutorial tomorrow, so we can do them in the class. How many questions do you have? 1. No problem. We'll do it tomorrow then. Which lesson was it? Yeah. I'd say a lot of people might have the same question. Which number? 5. There is no 5. You mean the last one?
No. 4.
Yeah. 5. Yeah. Definitely you'll do that tomorrow.